Understanding electricity. Who turned out the lights? You're sitting at home eating dinner and suddenly the lights go out. The refrigerator goes off. The street lights blink off. What happened to the electricity? On March 21st, 2001, situations like this happened all over the state of California. It was the first full day of spring and the weather was unusually warm. People turned on air conditioners and fans to cool off. These devices run on electricity, and they added to the electrical demand created by computers, lights, and other equipment already running. Suddenly, there wasn't enough electricity to meet the demand, so power companies cut power to some areas. This caused many problems, but a statewide power failure would have been far worse. Will this happen in California again? Can it happen in other parts of the country? To understand the answers to these questions, you have to understand how electricity works. This is a book about electrical power and how it affects all of us. So get ready to explore. You may find the experience quite shocking. Chapter 1. Going with the Flow. Do you know where electricity comes from? Even though most of us use it all the time, many people don't have a clue how electricity is produced. Simply put, electricity is a form of energy. Energy at work or power makes things move. You need energy to live and grow. The energy to run your body comes from food. Most cars get their energy from the gasoline they burn. Most of the energy that powers living things on Earth comes from our sun. Using electricity. Of all the different types of energy we use in our daily lives, electricity is one of the most important. What makes electricity special? It can be used to power many different things. It can give us light. It can keep us cool in the summer and warm in the winter. You can use it to make popcorn or watch your favorite movie. You can even use electricity to talk to your friends. Today, most people on Earth use electrical power. Electricity is used in homes, schools, businesses, and cars. In fact, people come up with new uses for electricity every day. It's hard to believe that a little more than 200 years ago, nothing ran on electricity. While people of the past knew about electricity, they didn't know how to tap into its power. Simple attractions. One of the first people to record experiments with electricity was Thales of Miletus, a philosopher who lived more than 2,500 years ago in ancient Greece. Thales discovered that if he rubbed a piece of fossilized tree sap called amber with sheepskin, something amazing happened. When he brought the amber near dried grass or feathers, these objects would jump and stick to the amber. In the year 1600, an English doctor named William Gilbert discovered that amber wasn't the only thing with this strange power. He found that other substances like rubber, glass, and wax also attracted things when rubbed. Static electricity. Did you know that the electrons that make electric power possible? Everything on Earth is made of very small particles called atoms. Atoms are made of protons, neutrons, and electrons. These protons and neutrons are packed together to form what's called the nucleus of the atom. Whizzing around the outside of the nucleus are electrons that can roam from atom to atom. The movement of these tiny electrons is electricity. Static is one form of electricity. For example, when Thales rubbed amber with sheepskin, some of the electrons from atoms on the sheepskin were rubbed off onto the amber. When many electrons collect on a surface, they crowd together. Eventually, some of them can jump off the surface or discharge. Sometimes you can get a shock from the static discharge. When you walk across a rug or dry weather, electrons rub off the rug and collect on you. As you get close to an object like a doorknob, the electrons can jump to it. Ouch! You get a zap and see a little spark. If you want to see static big time, just look at lightning. It's a static discharge too. Current electricity. Ever hear of a volt? When you buy a battery, you might look to see how many volts it has. The voltage of a battery tells something about its power. A volt is a unit of electrical pressure. It's named for the Italian scientist Alessandro Volta. Volta discovered a type of electricity called current electricity. Current electricity is a constant stream of electrons. In 1800, Volta did experiments with metal discs and fabrics that had been soaked in acid. He found that if he connected the metal discs with a wire, electrons would flow from one disc to another. This static of metals, fabric, and acid was the very first battery. The electricity-magnetism connection. During the early 1800s, scientists discovered a link between magnetism and electricity. Scientists had known for years that magnets attracted metals. Then scientists learned that the electricity flows through a wire. The wire attracts other metals, such as iron and steel. In other words, the wire becomes magnetized. When the current is turned off, however, the wire no longer attracts like a magnet. Wrapping a current-carrying coil of wire around a piece of iron causes the iron to become magnetized as well. When the metal is magnetized by electricity, it's called an electromagnet. The real breakthrough came in 1831 when English scientist Michael Faraday asked a simple question. If electricity could make wire and metal act like a magnet, could a magnet be used to make electricity flow in a wire? After many experiments, he discovered that the answer was yes. To get electrons to flow through a wire, Faraday moved a strong magnet past a coil of wire. He built the first electric generator, a machine that uses a magnet to produce current electricity. Why was this such an important discovery? Well, without a generator, almost none of today's power plants would be able to make electricity. How did Faraday's electric generator change our lives? Thinking like a scientist. Making a model. Models are representation of real-life things. When scientists want to try out new ideas, they often use models to help test the ideas. By using small models, scientists can get answers without spending time and money on huge experiments. Closing the circuit. All electrical devices from simple flashlights to the most complex computers operate on the same basic principle. It's called a circuit. A circuit can be thought of as a circle of electricity, which is how it got its name. A circuit is nothing more than a continuous loop or pathway through which electricity can flow. The most important part of a circuit is the conductor. This is the material that the electrons actually flow through, just as water flows through a pipe. Many different materials can be used as conductors. The most common conductors are metals, such as copper, aluminum, or steel. The opposite of a conductor is an insulator. This is the material that makes a very poor conductor, so electrons don't flow through it as well. Common insulators include glass, rubber, dry wood, and most plastics. Look at the electrical wires used to connect appliances to an outlet. You can see that they both have insulators and conductors. These conductors are on the inside, attached to metal plugs. The plastic or rubber around the wire is an insulator that keeps you from getting shocked. Chapter 2. Power to the people. When you turn on your lights, where does the power come from? Why does the power sometimes go out? What would you do if you were in the middle of a blackout? Today, it seems as if we have electricity whenever we want it. Plug in an appliance, flip a switch, and presto, you've got power. Night and day, power companies generate electricity to meet the needs of the growing world. As we've seen, however, the demand for electrical power can be greater than the supply. When this happens, people are faced with some serious questions. Sometimes power must be cut from a small area in order to save an entire region from a power failure or blackout. Most of the time, blackouts don't happen. Why? Because over the years, power companies have gotten together to form a large network. In this way, companies can share resources and supply power where the demand is the greatest. But today's modern power network didn't happen overnight. It took years to come together. Where did it all start? The place was Menlo Park, New Jersey, and the man who put it all together was Thomas Alva Edison. The Wizard builds an industry. Thomas Edison was known as the Wizard of Menlo Park. He invented more than 1,000 devices in his lifetime. Many were important in the creation of the electrical systems we use today. The best known of Edison's inventions is the electric light bulb, patented in 1879. In addition to being a great inventor, Edison was also a clever businessman. He knew that once people heard about the electric light, they would want it. So he also knew that the light bulb isn't any good unless you have electricity to make it work. During most of the 1800s, almost all electrical devices were powered by batteries, but batteries would not work for a large-scale lighting system such as the lighting of an entire city. So before Edison could sell light bulbs, he had to design a way to generate a lot of electricity. Then he had to get the electricity to individual homes and businesses. The task would have seemed impossible to most people, but not to the wizard. In 1882, Edison opened the world's first large-scale commercial power plant on Pearl Street in New York City. He produced power with generators based on the ones invented by Michael Faraday, a large steam engine and large steam engines to run those generators. The big problem was sending the electricity from the generator to the people who were going to use it. The first step was to dig up the streets to run electrical lines underground. This connected buildings to the power plant. Once Edison got the electricity into the buildings, individual circuits had to be put in each building. To make all these connections, Edison and his staff had to invent dozens of new parts such as switches, sockets, and fuses. Edison's pioneers. When Thomas Edison constructed his electrical power system, he did not do it alone. He gathered some of the best engineers and technicians he could find. He worked with them to solve problems as a team. Edison's employees were known as Edison's pioneers. They came from all over the world and all walks of life. One of them was Lewis Howard Latimer. Latimer was an African-American scientist and inventor who would become a major player on the Edison team. Lewis Latimer was born in 1848 near Boston, Massachusetts. The son of former slaves, Lewis began working at about the age of 10. After serving in the Civil War, he returned to Boston and went to work for a law firm specializing in patents. Saving his money, he bought drawing equipment and soon became an expert draftsman. In 1879, Latimer went to work for the American Electrical Light Company. While there, Latimer and a man named Joseph Nichols invented carbon filaments for electric light bulbs. The filament, the part of the light bulb that lights up, had been made of paper and other materials that burned out quickly. Latimer's carbon filament lasted much longer. Latimer was made chief electrical engineer of a company, and he traveled around the world installing electrical plants and lighting systems. In 1884, Latimer went to work for Thomas Edison. His main job at Edison Electric was to protect the company in patent lawsuits. In 1890, he wrote the first textbook on electrical power and lighting systems. During his life, Latimer created many inventions and developed many of the electrical systems we use today. Switches and circuit breakers. To make electrical systems like those installed by Edison and Latimer work properly, inventors had to come up with many clever devices. A switch is a device that can start and stop the flow of electricity, just as the faucet on a sink lets you start and stop the flow of water. But sometimes too much electricity can flow through a circuit and cause the wires to heat up. To protect wires from burning, inventors came up with an automatic switch called the circuit breaker. It shuts off the flow of electricity if the current gets too big. These devices help save many homes from fire. Building the power grid. As more electrical systems were developed, the demand for the power grew. In some areas, power companies did have enough electricity. Before long, power companies decided to connect different plants to different plants. This way, they could trade electricity between areas with extra supply and those with high demand. Today, we call this network system the power grid. Electricity on the move. From the power plant to you. Starts off at the power plant. Step-up station. At that station, the voltage is increased. If a large amount of electricity needs to travel a long way, the voltage is greatly increased. If a small amount of electricity needs to travel only a short way, the voltage isn't increased that much. 3. Transmission lines. From the step-up station, the electricity is carried along the transmission lines, which are made up of heavy cables supported by poles and towers. Step 4. Step-down station. At a step-down station, the electrical voltage is lowered. The voltage is lowered so it can be carried to smaller cables or distribution lines. 5. Distribution lines. Smaller cables carry electricity with lower voltage to homes and small businesses. 6. Home. Once electricity enters a home, it goes through the electrical system and provides energy to your outlets, lights, and appliances. Chapter 3. Fueling the next generation. Today, the demand for electrical power is greater than ever before, and it's growing. Where are we going to get all the energy we need? How do we solve the growing power problem? Why not just build more power plants? After all, that's worked in the past, so why not? Well, power plants are expensive. Also, how many people want a power plant in their backyards? But there's an even bigger problem, the environment. Today, almost 2/3 of the electrical power we use comes from power plants that use fossil fuels to make electricity. Fossil fuels such as oil, coal, and natural gas are burned to make electricity. Burning fossil fuels releases pollution and carbon dioxide gas into the air. As more carbon dioxide is released into the air, more heat gets trapped near the Earth's surface. The more fossil fuels we burn, the warmer the air around the Earth gets. So building fossil fuel plants is not always the best answer. Blow, wind, blow. Luckily, burning fossil fuels isn't the only way to make electricity. For example, people have been using power of wind for centuries. So why can't we use this energy to make electricity? Well, we can. In very windy places, power companies have installed dozens, even hundreds of large windmills. Windmills change the energy of moving air into clean electrical power. Wind power won't solve all the energy problems, but it can help meet some of the demand in certain places. Here comes the sun. If you're looking for a source of energy that doesn't pollute, look to the sun. The sun provides most of the heat and light to our planet. Since the late 1800s, scientists have been working to turn the sun's energy into electricity using devices called solar cells. The problem is solar cells are expensive, but scientists are hopeful that someday soon everybody will be able to take advantage of the sun's energy to make electricity. Energy from atoms. There are other ways to make electricity without burning fossil fuels. Scientists have learned how to change some types of atoms into other types of atoms. When this happens, a large amount of energy is given off. This energy from atoms, called nuclear energy, has been used to make electricity for more than 50 years. Today, about 10% of all the electricity used in the United States comes from this source. So why don't we build more nuclear power plants? Although nuclear power plants don't pollute the air like the burning of fossil fuels does, there's a major drawback. The waste products from nuclear power plants are dangerous and must be stored in safe places. Most people are concerned about the safety of the nuclear power plant, safety of nuclear power. A long way in a short time. Take a look around you and list the things that run on electricity. Now imagine life without them. That's how life was about 100 years ago. We've come a long way in the past century, and today scientists and inventors will help lead us in the future. Maybe you will become one of those leaders. After all, just like electricity, you've got the power. Thinking like a scientist. Models allow scientists to test ideas and learn how things work. If you wanted to learn about the electromagnets, use some large machines. You could build a smaller and simpler electromagnet to use as a model. To make a model, you first have to figure out what you want your model to show. If you wanted to show how a large machine uses an electromagnet to pick up objects, you could make a model to show how a small electromagnet can be used to pick up small objects. The next step in making a model is deciding what materials you need and how you will put your model together. Look at the notebook page pictured in the upper right to see how one student made a model of an electromagnet. How an electrical system works. It's hard to see how electricity moves from a power source into a light source in your home. But you could make a model that shows how this happens. Do this activity to see how electrical systems work.